Hi, welcome to Simply Current Affairs. We are starting with our next most important and interesting initiative, that is Current Affairs Hitlist series targeting Prelims 2026. As a part of this initiative, I will be covering 200 current affairs topics. While discussing those current affairs topics, I will be discussing the related static part as well. All these will be very important topics for our Prelims 2026 exams. I am doing this Hitlist series for many years in different platforms, and now I am doing it in my own platform, that is Simply Current Affairs. So I will be doing videos between Monday to Friday initially. As the exam comes closer, I will be increasing the number of videos which I will be sharing in a week. So today we will start with our first current affairs Hitlist topic, NISAR. NASA ISRO Synthetic Aperture Radar. As the name says, it is a collaborative effort of both NASA as well as ISRO. This is an Earth observation satellite, and what is significant about this is the first time a dual synthetic aperture radar has been used in an Earth observation satellite. That is why this topic assumes more significance. Sir, what is this synthetic aperture radar? Not able to understand, right? Let me explain that in detail from the basics. Before going further, these are my upcoming courses. One is 75/75, an exclusive current affairs program targeting Prelims 2026. The another one is economics, which is also targeting Prelims 2026. And another one is the current affairs and current affairs linked static test series. If you are interested, you can click the link given in the description to know more details. So we will move on to the topic. So to understand the synthetic aperture radar, first we will try to understand what is a radar. So to understand radar, let us take an example. Let's take these bats. See, we all know these bats are nocturnal animals. That means it will sleep in the day, it will be active in the night. In the night, in the darkness, to identify the objects in front of the bats use a technique called as echolocation. So what bats will do, the bats will emit sound waves. It will shout. Now these sound waves, it will go and hit the obstacle or any object in the front. Once it hits the object, there will be reflection of this, there will be reflection of those sound waves. Based on the reflection, how quickly the reflection comes back, in what direction the reflection comes back, what is the size of the reflection, based on that the bats will identify the object in front of it. So whether it is a tree or big animal or some small insect, everything the bat will identify using this echolocation technique. It will be emitting sound waves, the sound waves will hit the object, then from that the sound waves will be reflected, the bat will capture the reflection and then it will identify. The same technique is used in the radar. So radar means radio detection and ranging. Okay, radar system uses similar techniques. So what does radar do? So the radar system will be sending radio waves. There will be a transmitter which will be sending radio waves. These radio waves, once hitting the target, the radio waves will be reflected back. The radio pulses will be reflected back. So this will also have a receiver. There will be a transmitter, there will be a receiver. Now the receiver will receive the reflected radio waves. Based on the reflection, the radar system will identify the speed of the object, size of the object, in which direction it is moving, what is that object. Everything the radar system can identify. The difference between bat and radar system is, the bats are using sound waves, radar system will use light waves. Radio waves is also a light wave, but which is not visible for us. Radio waves is not visible for our naked eyes, right? So this is how radar system works. So radar means radio detection and ranging. A system uses radio waves to detect the distance, direction and speed of the objects, which will have a transmitter which will send out radio signals and a receiver which will detect the reflected signals. This can be used in tracking aircraft, vehicle, detecting ships, other objects, weather forecasting, etc. So in the synthetic aperture radar, you understood what is a radar. So now we will understand what is aperture. See, aperture's literal meaning is a small gap in which light passes through. See, you take your eyes. if you widely open your eyes, more light will be entering into your lens. When you are closing your eyes, then limited light will be going inside your eye lenses. So by opening and closing, you can change the exposure. You can change the exposure of our lenses. Similar thing happens in camera also. In camera, so you yourself can change the exposure. You can change the exposure. You would have seen this in camera settings, right? So if you are opening the shutter more, then the lens will receive more light. When you are reducing the aperture, the focus, the exposure, then the light will be coming less. So put it simply, aperture is nothing but a small gap through which the light enters. So aperture radar means what? Now radar is going to send radio signals, radio waves. So there is going to be a small opening through which radio pulses will be sent. Okay. Now what is synthetic aperture radar? Synthetic aperture radar. Now just imagine there is a mountain. Okay. There are many trees, beautiful trees. Okay. So now Guna is standing here. Guna is having a very normal smartphone, which has a normal camera. So now Guna is trying to take an entire picture. Guna takes a picture, but do you think that that picture will have highest definition? The picture will have some idea about the mountain. Now let's assume the distance between the mountain and Guna is 1 kilometer. So Guna is taking a picture. Guna will get the picture, but the picture may not be that great. It will not have best definition and all. But so if Guna is having a very big good lens, good camera means fine, but Guna is having a normal camera, normal smartphone camera. So now what Guna does, Guna is going little closer. Guna is going little closer. So Guna is going 100 meters closer. Now Guna is taking a photo. That photo will be relatively better. Now Guna is going another 100 meters closer. Now Guna is taking another photo which will be relatively much better. Now Guna is going 500 meters closer. But remember, as Guna goes closer, Guna will be getting better picture, no doubt, but Guna cannot capture the entire canvas. Guna cannot capture the entire canvas. Because as I go closer, I cannot capture the entire thing. Totality I cannot capture. But as I keep going closer and closer and closer, better definition photograph I will be getting. Better definition photograph I will be getting. So let's say Guna is 1 kilometer away, I have a bigger photo. As I go closer, I have another photo. As I go further closer, another photo, another photo, another photo, another photo. As I go more closer, I will be having better photo, minute details. Now imagine through a technology, I am stitching all these photos. I am stitching all these photos into one photo. I am stitching all these, I am superimposing all these photos into one single photo. Then imagine this photo, final photo will have much better definition, which will have a higher definition. When I superimpose, when I stitch one after another, I superimpose everything. How I will do it, sir? That is the technique, sir. That technique, so that is a technique through which I am stitching everything. Then with a relatively substandard camera lens, I am able to get a better image. So this synthesis of all these photos, right, using a radar system, which I am referring it as synthetic aperture radar. Synthetic aperture radar. See, look at here. Now this is the object. So there is a camera. So Guna is flying in this flight. So Guna is here taking photographs. Now Guna wants to capture this box. Okay. So now I am traveling this flight. At one angle I am taking a photo. At one angle I am taking a photograph. Okay. At any point I might not get a clear picture of the box. But imagine this, the photo taken from here, the photo taken from here, the photo taken from here, everything if I stitch it together, I will be getting a 3-dimensional image of the box. Yes or no? You are able to understand? So this technology where I am able to synthesize everything into one, that is what is going behind this synthetic aperture radar system. So even if you are having a relatively substandard camera or lens. Using this technology, you can take high definition images, right? And synthetic aperture radar system also has one more uniqueness. What is it? See, when compared to other optical imaging systems, it's a normal camera. When compared to normal camera optical imaging systems, the normal camera largely I'm saying, the existing optical imaging systems, they use sunlight. They use sunlight for taking the photographs. Okay, but synthetic aperture radar, since we have radar here, we will be sending radio signals. So radio signals will help us to capture the better images. Understand, the regular optical imaging systems, they use sunlight. For capturing the images. But synthetic aperture radar, it will send its own radio signals. The radio signals will be reflected back. The reflections will be catched by an antenna receiver, and that receiver will create the image. So what is the beauty, sir? Even at any point of time, when there is more clouds, or there is no clouds, or there are a lot of trees or artificial man-made structures, these radio waves can penetrate and they can will help us to capture better images. That is the advantage of synthetic aperture radar system. Right? So now I hope you are able to understand what is this NISAR. NISAR is an Earth observation satellite. Right? So this satellite is developed by NASA and ISRO. Now this satellite has synthetic aperture radar. Now what is significant about this NISAR is, for the first time an Earth observation satellite has dual synthetic aperture radar. That means the satellite has two radars. Okay, it has two cameras. Imagine. NASA gave one radar, ISRO gave one radar. Okay, the NASA radar is operating in L band. ISRO's radar is operating in S band. So what is this, sir? L band, S band. See, when I say radio waves, it is not one single wave. Radio waves is a group of waves. Okay, so you imagine piano. You have multiple notes, all put together we are saying piano. Like that, radio waves, there are multiple radio waves, a range of radio waves, all put together we say radio waves. Now this L band is also a radio wave. S band is also a radio wave. The difference is wavelength. Okay, so the difference is going to be the wavelength. L band is having a longer wavelength, a longer radio wavelength. S band will have a shorter radio wavelength. Okay, now NASA has contributed L band, ISRO has contributed S band radar. Now L band radar will be very effective to study those objects which are below the Earth's surface. For example, if you want to study about the groundwater, L band radar will be useful. If you want to study what is happening below the ice, below the Arctic ice, you want to know what is happening, L band. Now you want to know about the cropping pattern, the infections happening in the cropping pattern, you want to know about the aquatic ecosystem, you want to know about the forest density, right? Whether the forest is increasing or decreasing, you can go for S band radar, right? So NASA has given L band radar, ISRO has given S band radar, both put together is a dual SAR, which is a part of this NISAR. Because of this dual SAR, this becomes very, very important because it's the first time, right? And India, it was news recently only, India was launching. So India took the responsibility of launching it from the Satish Dhawan Space Center, Sriharikota, with the help of GSLV rocket. We launched this satellite and we placed this NISAR satellite in sun synchronous orbit. Sir, what is the sun synchronous orbit? But before that, we will go through the slides. Then I will explain about the sun synchronous orbits. Right? So, synthetic aperture radar is an advanced imaging technique which was first developed in 1950s. So, unlike the regular optical imaging, it will send radar signals to Earth's surface and captures their reflections. Okay? So, it is ideal for 24/7 monitoring in all weather conditions. So, NISAR, as I said, is an Earth observation satellite developed by US Space Agency NASA and India Space Agency ISRO. Agreement signed in 2014. It will map the entire globe in 12 days. Right. So, it is the first satellite which will have dual frequency synthetic aperture radar. NASA has given the L band radar. ISRO has given S band. Right. So, the L band, which will be penetrating into the vegetation, soil, ice to monitor the ground deformation. S band will capture high resolution surface details as crops, water bodies, urban infrastructure, etc. And more importantly, this will have a 39-foot radar. Okay, the radar, antenna. This antenna is what will capture and will give us the better images. Alright. So, objective. So, the radar is capable of reading what is going above the earth, below the earth. So, to know about the meltdown of Arctic ice, to know about the density of the forest, whether the forest cover is increasing or decreasing, to know various disastrous activities even before volcanic eruption, we can understand there's a possibility of volcanic eruption. Okay, about the deformation caused by the earthquake, which can be understood. Aquatic ecosystem can be studied, groundwater can be studied, coastal erosion can be studied, ocean currents also, that pattern can also be studied. So, application, sky is the limit, right? That is why this becomes very, very important. So, why it was in news? So, the satellite was successfully launched at Satish Dhawan Space Center at Sriharihota using a GSLV rocket. It has a 5-year mission life and it will be giving you valuable data. So now we will briefly discuss about this sun synchronous orbit. Sun synchronous orbit. See, there are many orbits. Orbit is nothing but a defined orbital path which will come around the planet. Okay, so we have low Earth orbit, we have middle Earth orbit, we have geostationary orbit, geosynchronous orbit. Okay, we also have another orbit called as polar orbits. Now, low Earth orbit is at a distance of 400 to 1000 kilometers. Middle Earth orbit roughly 2000 plus kilometers. Geosynchronous, geostationary roughly 37,000 kilometers. Okay, so forget about this numbers and all. The orbits we will discuss in detail a little later. We will discuss about sun synchronous orbit. Now, this is polar orbit which will be running in north-south direction. Okay, so pole to pole it will be running. Sun synchronous orbit, it is also a polar orbit. Okay, similar to that of polar orbit, it will run in north-south direction, but there will be a small tilt. See, look at here. So this is the, I'll choose some other color. Okay. So this is the north-south. Okay. The sun synchronous orbit is slightly tilted. It is slightly tilted from this north-south direction. This tilt is essential. Because only then, so here we have our satellite. So we have to sync our satellite with the solar time, with the sun solar timing. See, let's assume, so Guna is standing here. Today at 12 p.m. the sun is exactly overhead. But tomorrow, the sun might be exactly overhead either at 11:55 a.m. or 12:05 p.m. Day after tomorrow, the time can vary. Okay, so don't think that every day at 12 p.m. the sun will be above your head. Today it may be at 12 p.m. Tomorrow it might be 11:55. Day after tomorrow it might be 12:05. See, the timing in the earth, the timing which we follow in the earth and the timing of the sun is not in sync. It's not in sync. So assume that today 12 o'clock I go outside. Sun is above me. Tomorrow 12 o'clock I go outside. Sun will not be above me. Day after tomorrow I'll go at 12 p.m. outside. Don't think sun will be exactly above you. Above me. Okay, that's not going to happen because the timing of sun, the timing of our watch is not in sync. We have to sync it. We have to sync it for Earth observation satellites. For Earth observation satellites, it's better to follow the solar clock so that it will be very, very precise. So for this precision, we have kept the NISAR satellite in the sun synchronous orbit. Right? So yes, this is about the sun synchronous orbit. I have given information about this as well. So it is at a distance of approximately 600 to 800 kilometers. So it helps in Earth observation, mapping, environmental monitoring. So this is about the sun synchronous orbit. So we have discussed about radar. We discussed about synthetic aperture radar. We discussed about NISAR. We discussed the contribution made by NASA, contribution made by ISRO. We also discussed the applications of this NISAR. And we also said this NISAR satellite is placed in sun synchronous orbit. So briefly we discussed about the orbits as well. Right? I hope you got clarity on this topic. Very, very important from our exam point of view. So now I'll give you an exercise. See, in the comment section, now you got clarity on the topic what we discussed. In the comment section, you construct a multiple choice question. Based on our discussion, you create a multiple choice question on UPSC standards. See, once we start setting the questions, our conceptual clarity will improve and you will understand the neck of the UPSC setter also. So that lines will help you to understand and revise better. So you set a multiple choice question, I will solve it, I will give my comments. Let all other subscribers who are watching this video, let them also solve it. Everyone, I want everyone to construct a question, interesting questions based on this. See, you want to extend some static portions and construct a question, you construct, no problem. I'll give my feedback. Right friends, I hope you are liking all our initiatives. So share your feedbacks. Your feedbacks in the comment section is what is motivating us largely. So I will see you in another video. Till then, bye. Take care from Guna Mathivanan.